okay? All right. Here is a link to a video that I've put also in Brightspace. If you haven't already, please go ahead and watch it. I think these videos are really good at illustrating some of the concepts, especially the more abstract concepts that we describe. So definitely go ahead and watch these videos. They're also posted in Brightspace. Okay, I'm going to pause here and see if we have any questions. And then we're going to look at this flow chart that sort of describes what we have just said. So again, we're going to just reiterate everything that we've said, just in a different way. Okay, so let's kind of walk through this, and please stop me if anything is confusing as usual, but I'm going to kind of go through each slide and talk about the sequence of events from the standpoint of this flow chart. So we start with a threshold stimulus. Okay, we know this has to be negative 55. So I'm going to go ahead and actually put that in here. Negative 55. Okay. What happens next? Next, we have a depolarization of the membrane. Okay. In other words, sodium channels open up. So sodium channels open up, specifically the activation gates open up. Remember, at rest, the inactivation gates are already open. So the channel is closed, but it is capable of being opened if a strong enough gradient potential comes along. Membrane permeability for sodium increases. In other words, more doors for sodium opens up. Sodium can rush into the cell, okay, according to its ECDF. Sodium rushes into the cell. That's going to increase the net positive charge that's accumulating inside the cell. And so that, in essence, is what we mean by depolarization, a positive membrane potential change. That's going to be a positive feedback example because the opening up of sodium channels actually encourages more sodium channels to open up, right? And that's going to happen continuously, moving us further and further away from our set point, which is negative 70. And then we're also going to have the delayed 1 millisecond timer go into effect or set off, right? That timer is going to set off. So upon the opening up of sodium channels, upon the opening up of the inactivation gates at depolarization, a 1 millisecond timer starts. And so after 1 millisecond, the inactivation gates will subsequently close. Okay. After those gates close, sodium permeability is going to decrease. This should have a down arrow. For some reason that got missed, but definitely put it in your notes. This should have a down arrow here. Sodium's permeability decreases. The membrane's permeability for sodium decreases. Okay, and so that means sodium flow is going to stop. The movement of sodium is going to decrease as those channels close and as the membrane permeability decreases. And that means that the net positive charge in the cell is also going to decrease. Okay, that is going to trigger the repolarization. But we know that something else is happening that is also going to trigger or help the repolarization as well. That is the 1 millisecond timer for potassium channels as well. So remember that we said that potassium channels, they only have one gate, and it is a timed and voltage dependent gate. And so also at depolarization, 2 timers are going off. The 1 millisecond to close the inactivation gates, also the 1 millisecond to open the potassium channels. And what this is ensuring is that these 2 events are synced. They're happening simultaneously. They're happening at the exact same time. This is why the timing is so important. This has to happen synchronously at the exact same time And so the 1 millisecond timer ensures that the inactivation gates close at the exact same time that the potassium channels will open up. All right, so potassium channels open up, membrane permeability to potassium increases. Again, an arrow should be here. All right, this should be an up arrow as that permeability increases. Okay. Potassium can start to flow out of the cell as its permeability increases, and then that will also work towards decreasing the net positive charge in the cell or encouraging repolarization. Okay, this part of the action potential, the downstroke or the repolarization we mentioned, this is an example of negative feedback simply because this event, this change, helps to get us back to our resting value or our set point, which is -70. Okay. All right. Let's illustrate this in another way. Okay, so I keep reiterating that we're not introducing anything new. We're just looking at the action potential in a few different ways. It can be a very difficult, abstract idea to wrap your head around. And so we want to think about it from different perspectives. And so we're going to just look at it from a flowchart perspective, from the permeability perspective, and now we'll look at it from a graph perspective. So exactly what's happening in each of these phases. So let's start off at rest. All right, this is where our graded potentials are important. We'll talk about these two terms coming up. This is an Ipsp or an Epsp, and I'll talk about what these mean coming up. But this is essentially a negative membrane potential change or a positive membrane potential change. In other words, depolarization or hyperpolarization. A depolarization for the Epsp, hyperpolarization for the Ipsp. So these types of changes can determine if we are close enough to -55. If we are, we have a depolarization, right? This is our threshold value right here. Sodium channels open up. What does that mean? Activation gates are open. Inactivation gates are also open, and sodium can rush into the cell. The membrane potential becomes more positive as it does that. It tries to approach the equilibrium potential, but that doesn't actually happen because at +30, a 1 millisecond timer is already in effect, right? That 1 millisecond timer is in effect to where we have a reverse of the gating mechanisms, all right? During the depolarization, potassium channels are also closed. But again, think about that timer. That timer has gone off. And so it's 1 millisecond before the channel will actually open up. Repolarization comes along. So this is what we have at +30. The timer has resulted in two things happening at +30. The inactivation gates close and the potassium voltage gated channels open. And so now we see the membrane potential become more negative as sodium is no longer able to move because its channel has closed, but potassium is now able to move. And as it leaves the cell, the membrane potential slowly not slowly, but steeply becomes more negative, actually overshooting the resting membrane potential. Hyperpolarization, which is the end of the action potential, is where potassium channels are still closing. The membrane potential is now -85, and then it will slowly return to rest with the help of the sodium-potassium pumps. Okay. Right. So we will speak about two different types of events. We will talk about two different refractory periods or periods after the action potential where we're not able to fire another action potential, the absolute and relative refractory period. But these are the two events that are responsible for that. So in the repolarization phase, we cannot fire another action potential. Why? Because our sodium channels are inactivated. They are closed and incapable of being open because both of the gates are closed. So even if we had another graded potential come along and it was strong enough, it was negative 55, it's still not going to be able to open up the sodium channel. So we physically cannot fire another action potential in this state. This is called the absolute refractory period. Below, in the hyperpolarizing phase, this is going to be considered the relative refractory period. Why? Because now we're getting back to negative 70. The sodium channels are going to eventually become activated, where the inactivation gate is open, but the activation gate is closed, right? That is the state of the channels at rest. And so it's going to be harder to fire another action potential because there's still so much potassium inside the cell, and it's still trying to recover, but it's going to be possible. It's going to just take a stronger stimulus. So these two events will be the difference between the absolute refractory period here and the relative refractory period here, right? Where it's possible, but it's just harder. Okay. Here's a nice study table for you. Again, I'm going to encourage you to go over this study table, try to block out some of the columns, and try to use this as a way to recall some of the events here. Someone's asking me to go back to this slide, so I'm going to just go back here for a minute. Someone else is asking, I think I missed this, what does Ipsp and Epsp stand for? So we haven't talked about this yet. Ipsp is an inhibitory postsynaptic potential. And we'll talk about exactly what that means, but that is a negative membrane potential change. In other words, a hyperpolarization or hyperpolarizing event. Epsp is an excitatory postsynaptic potential. So it's just a way for us to further describe the graded potentials. And we'll talk about what those are when we look at the synapse in our next unit. All right, so Ipsp inhibitory postsynaptic potential, Epsp excitatory postsynaptic potential. Okay. All right. Another study table, this one's really nice because it helps to distinguish the graded potential features from the action potential features. So their location, where they happen on the neuron, the strength, right? Weak versus strong, all or nothing is another way to describe the strength. And this 100 millivolts value, just to describe where we get this number, this is the change from negative 70 to positive 30. Right? So an action potential is always that magnitude, 100 millivolts. It always goes from negative 70, right? Negative 55 getting us to threshold, and then always all the way up to positive 30. And again, the direction of change, the ability for summation, we'll talk about this coming up, but action potentials do not have the ability to sum. We cannot add or accumulate action potentials. They cannot aggregate, right? They cannot add or be added to each other. It's one, recover, another, recover, another, recover. There is no adding or addition to action potentials. There is for graded potentials, all right? The refractory period, so graded potentials have none. Action potentials do have two. The channels that are involved, so for the graded potentials, it's going to be ligand gated. And we'll talk about what this means some more when we look at the synapse, what has to happen for the stimulus to be reached on the soma as far as the graded potential. There's a certain ligand that has to bind. For action potentials, this is the voltage gated mechanism, and we did look at that. So this is a really nice table for you to compare the events. Again, you can easily see questions that ask you about the different features of these two types of potentials.